Square Matrix Introduction. Hello, everyone. Let's begin our lesson on matrices. First, it is important to understand that in the study of matrices, we classify different types of matrices based on their dimensions, which refers to the number of rows and columns they contain. Among these various classifications, one of the most fundamental and frequently used types that you will encounter in your mathematics course is the square matrix. Now, you might wonder why we use the term square. A matrix is termed a square matrix because its dimensions are equal, which creates a balanced, square-like structure of elements. In the following slides, we will move from this general concept to the specific mathematical conditions that define a square matrix and explore how they are used in real-world scenarios. Understanding the concept. Now that we have a basic introduction to square matrices, let's dive deeper into how we actually identify one. To do this, we need to look at the order of the matrix. In general, the order of any matrix is written as m by n, where m represents the number of rows and n represents the number of columns. So, what is the specific condition for a matrix to be considered square? Quite simply, a matrix is called a square matrix if and only if the number of rows is exactly equal to the number of columns. In mathematical terms, we express this condition as m equals n. Because the dimensions are identical in these cases, we can simplify our terminology. Instead of always saying the matrix is of order n by n, we can more concisely refer to it as a square matrix of order n. Let's now look at the general notation you will encounter in your textbooks. If we have a square matrix named A of order n, it is represented as A equals a sub ij, with the dimensions noted as n by n to break this notation down further. A is simply the name we give to the matrix. The term a sub ij represents the specific element located at the ith row and the jth column. Finally, the n by n notation serves as a reminder that both the row count and column count are the same. Once you are comfortable with this conceptual framework and the notation, we will move on to the next slide to see how this is applied in a real-world scenario using a distance matrix. Real-world example, distance matrix. Now that we have established the theoretical definition of a square matrix, let us apply this concept to a real-world scenario to see how it works in practice. Imagine you are tracking the distances between three different cities, City A, City B, and City C. To organize this data efficiently, you can create a table where both the rows and the columns represent these three cities. Let us begin with step 1, where we identify our specific data points. The distance from City A to itself is 0 kilometers. The distance from City A to City B is 50 kilometers, and from City A to City C, it is 80 kilometers. Moving to the next city, the distance from City B to City A is 50 kilometers, from City B to itself is 0, and from City B to City C is 30 kilometers. Finally, the distance from City C to City A is 80 kilometers, from City C to City B is 30 kilometers, and from City C to itself is 0. In step 2, we arrange all this gathered data into a matrix, which we will label as matrix D. This matrix is structured with 3 rows and 3 columns. The first row contains 0, 50, and 80. The second row contains 50, 0, and 30. And the third row contains 80, 30, and 0. Now, in step 3, we analyze the dimensions of this matrix. By counting the horizontal lines, we find that there are 3 rows. By counting the vertical lines, we find that there are 3 columns. This leads us to step 4, our conclusion. Since the number of rows, which is 3, is exactly equal to the number of columns, which is also 3, the distance matrix D is a square matrix of order 3. This is a perfect practical example of the condition we discussed in the previous slide, where the number of rows equals the number of columns. Keep this structural requirement in mind, as we will move on to discuss some common pitfalls students encounter when identifying these matrices. Common mistakes to avoid. Now that we have seen a practical application with the distance matrix, let us move on to some common pitfalls. It is important to address these misconceptions early to ensure your understanding is precise. First, be careful not to confuse the term square with the actual values contained within the matrix. Some beginners mistakenly believe that a matrix is considered square if the elements inside it are square numbers, for example, numbers like 1, 4, 9, or 16. This is incorrect. Please remember that in linear algebra, the term square refers strictly to the dimensions, meaning the number of rows and columns, and has nothing to do with the numerical values of the elements. Secondly, let us discuss the risk of miscounting dimensions. As we established in our earlier slides, you must always count the rows first and then the columns. For instance, a matrix that has 2 rows and 3 columns, which we would describe as a 2 by 3 matrix, is not a square matrix, even if it appears compact. Always verify that the count for both rows and columns is identical. Finally, pay close attention to your notation. When describing a general matrix, we use the notation m by n, however. For a square matrix, you should specifically write the order as n by using the same variable. N, for both dimensions, you are mathematically stating that the number of rows and columns are equal. Once you have a firm grasp of these distinctions, you will be well prepared to review the final key takeaways in the next slide. Key takeaways. Now that we have explored the definition, worked through a real-world example with the distance matrix, and identified common pitfalls, let us summarize the key takeaways to ensure you have a solid foundation. First, let's revisit the core definition. A square matrix is any matrix where the number of rows is exactly equal to the number of columns. Mathematically, if we use m to represent rows and n to represent columns, the essential condition for a square matrix is that m equals n. In terms of terminology, while you can describe such a matrix as being of order n by n, it is more common and concise to simply refer to it as a square matrix of order n. Regarding the notation, we represent this as capital A equals the element, a sub ij, in a matrix of size n by n. This notation serves as a reminder that the row and column counts are identical. Finally, it is important to understand why we focus on these specific matrices. Square matrices are fundamental because they are the only matrices that allow us to perform advanced operations, such as calculating the determinant and finding the inverse of a matrix, topics which we will dive into in our future lessons.